The reactions of esters. So esters are the third carboxylic acid derivative compounds, and let's talk about their reactions. Now, esters are easily converted into carboxylic acids, amides, but cannot be used to form acid chlorides or anhydride, meaning here's your ester, can't go this way. But this is easy. So again, can't happen unless you have, once again, special conditions. Now, while we're here, notice that esters and carboxylic acids are as reactive as each other, right? So they have the same reactivity. So the question then you might have is, can the reaction take place between them? And the answer is yes, but they are at equilibrium. And the only way to drive the reaction into one direction or the other is to apply Le Chatelier's principle. Le Chatelier's principle talks about, if you recall from Gen Chem 2, talks about that you can actually create an imbalance, meaning shift their equilibrium into one place if you add or remove compounds or substances. So we're going to talk about that when we get there. So now the first reaction, a very, very important reaction, is called the hydrolysis of esters, meaning esters are turning into carboxylic acids. So the hydrolysis of esters is a very slow reaction because water is a poor nucleophile and esters have 4 leaving groups, the alkoxide, the OR group. These reactions are therefore always catalyzed in the lab using acid or base. So you have acid catalyzed and you have base catalyzed. Also, because the stability of esters, carboxylic acids are similar, the reaction has to be driven to completion using Le Chatelier's principle. So as I mentioned before. So let's talk about this reaction and be prepared to write the mechanism for this because it is a bit longer than the ones we saw previously, at least in this chapter. So if we have an ester and if we react this with water, and notice how we have acidic conditions. So that's a catalyst. We are able to generate a carboxylic acid plus an alcohol. So you have an alcohol in this case. So let's talk about the mechanism. So here we go. We're going to redraw this. Now, the first step, because the reaction is slow, is you need to make the carboxylic or the carbonyl group more electrophilic. So the reaction involves, and you've seen this mechanism before, at least this first step of the mechanism, is the carbonyl oxygen attacking the acid, the proton becoming protonated, which, if you recall, this makes the carbonyl carbon more electrophilic. Okay, now water can attack as a nucleophile. and a positive charge on the water. So now another water molecule will serve as a base to deprotonate the added water molecule. So you are now at this point. Now we have an acid as a catalyst. Obviously, it came also from here. So we're going to draw this right here, the hydronium. So now the OCH3 group will be protonated to make it a better leaving group. So there's now a positive on this oxygen, which makes it an ideal leaving group. Now, it doesn't matter which one you choose. You can choose this oxygen, this alcohol group, this hydroxy group, or the one on the top. I'm going to choose the one on the top to remain consistent with the carbonyl oxygen position. So there's two lone pairs here, but one of them comes down. And now this is kicked out as a leaving group. Now, finally, we need to deprotonate this carbonyl oxygen. So that's where water comes in. Deprotonates it, thus regenerating the acid. And of course, making the carbonyl compound, which is the carboxylic acid. So again, look what we made here. We have H3O plus, and of course we have the alcohol, HOCH3, which is the same as CH3OH, methanol in this case. Of course, it applies to other alcohols. Now, you're wondering once again why did we protonate the carbonyl oxygen? So again, recall that this the protonated carbonyl is more electrophilic than the unprotonated ester in this case, or the carbonyl group, which is of course the ester. We already established that because again, you can have resonance, electrons moving toward the oxygen to offset that positive charge, making the carbon more positive, which is electrophilic. And then the other thing is the reaction is reversible and must be driven to completion. How do you do that? So Le Chatelier's principle says, so what you do is you do excess water or remove the alcohol as it's formed. All right, so let me go back to this. Le Chatelier's principle, if you recall from Gen Chem 2, says that if you want to drive the equilibrium into one direction, into a specific direction, you have to do one of the following things, or you can do multiple things. If you would like to drive the reaction forward toward the carboxylic acid, you have to add more water. The more water you add, now to create a balance, the equilibrium is going to shift that way to counter that action. If you want to also move it forward or keep the reaction moving forward and to make more of the OH, you remove the alcohol. You keep removing. As you're removing, the other side has to work even harder to make more of the alcohol. So again, that's the counter move to recreate, to reestablish the equilibrium. So that's what Le Chatelier's principle is saying here.